Okay, so not so sharp. I think this project is something wrong. The other cars is okay, but this one is a bit, the intensity is not strong enough. Okay, so good afternoon, everyone. So we continue our lecture in audio processing. So in last lecture, we stopped at here, which is the Nyquist theorem. Okay, we stopped at here, which is the Nyquist theorem. So I've been mentioned the Nyquist theorem for several times, even though in image processing, because the Nyquist theorem is not only applicable to the is not only applicable to this audio processing, because audio, images, video are all signal. Okay, so it is applicable to signal processing. So signal processing, I believe you already been, I mean, so this causes, I think, signal processing, right? By Dr. Yo, I think. So those would be the fundamental of signal processing. And later on, in MTAA, we will more focus in three applications, which is the images, the audio, and the video. Okay. So Nyquist theorem is named after Harry Nyquist, a famous mathematician who worked at Bell Lab. So Bell Lab is a lab which is very famous, and many scientists or mathematicians from there awarded with the no, Nobel Awards lah. Okay, so originally it is owned by Nokia. So later on, transferred to some other people lah. Okay, so the Nyquist theorem states sampling frequency is required to be at least twice the maximum frequency of the input signal in order to construct back the original analog signal. So the main purpose of the Nyquist theorem is actually to create, to define the condition where you can create or construct back the original analog signal. So let's say last time we already, for example, you have this analog signal. So what would be your sampling required or the frequency required in order for you, when you convert this analog to digital, this is analog to digital. So uh, in what conditions you can actually reconstruct back this to the original, not really identical, but approximate to the analog signal. So this would be the condition where the Nyquist prove that it is essential to fulfill. If you did not fulfill this one, so perhaps you will have a condition known as the frequency aliasing. Is it frequency aliasing? Yeah, aliasing, frequency aliasing. So frequency aliasing is a condition whereby you have, I mean, the digital signal is now suffer from undersampling. Okay, so let's see. Uh, if a signal is a band limited, that is, it has a lower limit f1 and an upper limit f2 of a frequency component in a signal, then we need a sampling rate at least 2 times f2 minus f1. Basically, it's the higher frequency minus the lower frequency in order to get the gap. Okay, after you're getting the gap, you multiply by 2 because at least twice. Okay, if you have 4, 5, 6, 7, it's okay. At least you have 2. Okay, the higher the gap, the higher the value you assign, the better approximation. Okay, but nonetheless, if you increase higher than this 2, then of course you need more size to store the data. But if you have less than 2, which means you do not fulfill this condition, then perhaps your signal, your digital signal will be suffer from undersampling. Okay, let's look into the some of the example. In particular, the discrete time series derived from two-course sampling. Two-course, which means your sampling is too less, or undersampling of a continuous signal actually contain contributions from high frequency component of that continuous signal. So those high frequency fall back into the spectrum of the discrete time and appear as low frequency. Perhaps this is a bit difficult for you all to comprehend. So we continue first. The phenomenon that is caused by undersampling in the continuous signal is termed as frequency aliasing. So frequency aliasing is the terms that we actually use to describe this condition. If you have undersampling, we call this as frequency aliasing. Okay, so let's look into this one. So this page is actually to explain this one. Okay, so you have your frequency, for example, 1 second. So which means you have 4 periods in 1 second. 1, 2, 3, 4. Okay, so this is some fundamental in signal processing. So in order to get the period 1 divided by 4, right? So 1 divided by your period, you will get 4 hertz. So which means this is 4 hertz. So let's say in the Nyquist theorem, it's say that you must do time the maximum frequency, right? So in Nyquist theorem, you have 2 different conditions. In first condition, you just have the maximum frequency. The another condition, you have F2 and have F1. Okay, so only 2 conditions. The first condition, for example, like this one. So the frequency is 4 hertz lah. Okay, so which means you 2 multiplied by 4 hertz, you will get 8 lah. Okay, so for this one, you have such a gap lah. For example, the upper frequency is 4, lower frequency is 2, so 4 minus by 2 lah, something like that. Okay, so for this condition, we are actually referring to this one as the first one. Okay, so the frequency would be 4 hertz. So if let's say you change the value of 2 into 1, example, look into this note. Example of sampling at 1 time the frequency, which is 6 sampling point. 1 times, 1 time is 4 sampling point. Typo here, 4 sampling point. So you divide the interval here by 4. So you get 4 sample only. So first sample, second sample, third sample, and the fourth sample. So later on, you reconstruct this one by joining each of the point, so you will get a straight line. Okay, so a straight line is definitely wrong, okay, because your original signal is something like this one. But after you convert to digital, this is analog signal. After you convert to digital, you get only one line. Definitely wrong. Okay. So what's happened when we increase the sampling rate to 1.5, 1.5. Okay. So we have 4 hertz, right? 1.5 multiplied by 4 hertz is what? 6. So we get 6 sample. Okay. So we divide 1 second into 6 interval. The interval must be same. So you get 6 sample. 1, 2, 3, 4, 5, 6. You will get something like this one. So when you actually connect this line together, it is still under sampling. Why? Because you have how many period here? 1, 2, 3, and 4. For this one, you have only how many period? Maybe only 1.5 only 1.5 period. So again, this is under sampling again. So let's say you fulfill the Nyquist theorem, you get 2 times the frequency. So the frequency is 4, right? So 2 times, which means you get 8 sample. So again, divide 1 second by 8. So first sample, second, third, fourth, fifth, sixth, seventh, and 8. So after that you reconstruct back, you will get something very similar. We cannot say that it is exactly the same, but at least it is much more simpler than that. So if let's say you have more and more times of sampling, for example, I sample at 10. So 10 multiplied by 4 would be 40. So which means you get 40 sample from your analog. So you will get a better illustrations of your signal. Okay. So this is the what is meant by the Nyquist theorem over there. So if let's say you have for example, you have a 4 frequency is 4 okay. So if let's say your sampling rate is less than the 2 multiplied by the maximum frequency, so for sure you will suffer from undersampling. Okay, so this is the main main purpose of the Nyquist theorem lah. Okay, so that is all for the Nyquist theorem. So signal to noise ratio. I believe you all been heard about SNR quite some time, so because I think this is quite common in engineering, especially in signal processing, because SNR is not only common in signal processing, but it is also being used in the image processing. Nonetheless, of course, the way we use in the image processing will be different because in image processing, the noise, the information representing the noise and information representing the signal is different. So that is why we still using the same, because SNR is actually ratio only. Signal to noise ratio is actually referring to uh, useful information towards noisy information, which is irrelevant information, and we compare the ratio. So if the ratio is higher, which means your signal ratio is greater, your noise is lesser. Okay, but it's very rare to have no noise in the system. Okay, it's very rare. No matter in image, audio, or video, it's very rare for you to get no noise at all. Okay, so we only can determine if the signal to noise ratio is very high, which means you have more signal, you have less noise. And if your signal to noise ratio is 1 to 1, which means you have 200 noise and you have 200 signal, which means the useful information and the irrelevant information or disturbance in your input data is equivalent the same, which is very noisy actually. Okay, which means that you go the market and buy 10 apples, 5 is already spoiled, something like that. So yeah. So in any analog system, random fluctuations produce noise added to the system and then measure voltage is thus incorrect. Actually, in the analog system, everything being measured is in voltage. No, actually, it's not only limited to the analog system. Eventually, in our human body, we are actually sending all the impulse using electric voltage as well. Of course, not the voltage that you can feel electric shock, something like that. But the impulse is actually sending in terms of synapse, the chemical to try trigger the impulse to send from one location to another locations. And in analog system, everything is in voltage. So when you convert, especially when you convert from analog to digital or digital to analog, or maybe you connect the audio from the speaker, from the mic, collect your sound, and sampling it, convert to audio, and then reconvert back to the speaker to amplify it, and etc. All this conversion is actually introduce noise. Just that the noise is it uh, very annoying, very significant, or how? So that is why when you have two audio, this is quite common when you have two audio system, bring together, and especially two mics when you go for karaoke and you have two mics on together and the setting is incorrect, so you would suffer from a humming effect. So the humming effect is not the humming effect itself is not from your signal noise, but the humming effect is from any the signal receiver, something like that. So which is introduced to your to the signal that going to be transferred or audio to be transferred. So it is not something that corrupt a specific. For example, I play a song, for example, Negaragu. So if you use a particular the Negaragu song, national anthem song, initially it has no noise corrupted, but when you play, where using a very lousy audio system, it may introduce noise, or maybe you put your handphone very near to the speaker. It may, when you receive SMS or something else, that would be sort of noise like the sparkling sound, something over there. All those noise is not from the national anthem itself, but introduced from all different kind of hardware, the audio system introduced to your song or the audio to be played. Okay, so we will look into that one in the subsequent slide. So all this type of noise is known as signal to noise ratio. Okay, but of course we have another noise which is signal to quantization noise ratio. Okay, so that one is a bit different. So SNR is measure the quality of the signal. So the higher the SNR, the better it is. So SNR is usually measured in dB, where 1 dB is a tenth of a bell unit of for sound. most of the time the everything regarding the audio, the sound, the noise would be measured using dB lah. Okay, so this is the in any system we would have a noise. Just depends on how significant is it, or it is negligible. Okay, there is no such thing that no noise in a system. It's impossible. So this is the noise of quantization. Quantization is that I hope you all still remember. You know, when you have maybe we make it simple. Uh, okay, something like this. So when you convert it to, even you use a very high sampling rate, you would still introduce the quantization noise. How is quantization noise being introduced is that all those gaps here would be your quantization noise. No matter how I mean how many sample you're going to take, you know, maybe I take 2,000 times the maximum frequency, you will still inevitable to such kind of noise. Okay, because when you're converting the analog, you know, the analog to digital, because in digital we always need to convert it in a district data lah. Okay, so all this green color here would be the quantization noise. Okay, just depends how severe or how significant is the noise. All right. So basically, this would be a useful signal lah. For example, your song, your video. So this is your signal. I mean, this part is your signal, and the part in red color would be the noise of quantization. So you have signal to quantization noise ratio, SQNR. So in your examination, please be extra aware. Do not simply just, oh, SQNR or SNR both are the same. It's different. SNR is in general noise, okay? But SQNR is in quantization only, okay? So for digital signal, we must take into account the fact that only quantized value are stored. So-called the quantized value is that you convert to digital, okay? We don't process or analog, we process digital. So for a digital audio signal, the precision of each sample is determined by the number of bit per sample. So typically 8 or 16 bit. Aside from any noise that may be present in the original analog system, additional error result from quantization. But of course, the noise from quantization is invisible. Just that we're not sure how severe it is. But we can actually to reduce the noise from the ambient environment, for example, construction. You know, you go somewhere quiet to do the recording and etc. So if voltage are in the range of 0 to 1, but we have only 8 bit in which to store the value, we effectively force all continuous value of voltage into 256 different value, which means that if you have 0 to 1, although 0 to 1 is only, you know, two integer, but you have, you know, 0.001, 0.002, and so on, you know, many infinity value over there from in the range of 0 to 1. Okay, but because we are using 8-bit, for example, you can only assign 256. The value in 256, as in the image processing, you have 256 pixel, which means starting from 0 to 255, right? Why that is 256 is that you have only 8 bit. If let's say you have 16 bit, of course you have a better lah. But that is by using 24 bit, we have, you know, 8 times 8 times 8, we can create like 65 million of color already. That is based on the probability. So we don't need I mean, higher bit is not really useful actually lah. So for this one, because you have so many flat numbers between 0 and 1, but you only can assign 256 space for this value. Okay, so this is inevitable to introduce round off error, as in the image processing as well. We always have round off error, but the round off error somewhat is negligible, I would say. Although it is not really noise, it is called quantization noise. So this is important because uh, it is a noise. Anything that we don't want, we consider that as a noise. But quantization noise is inevitable, is that we must process only the digital data, no matter in image, video, or audio. So we must convert everything from analog to digital. So when you convert analog to digital, the the conversion itself may introduce noise. So those are called quantization noise. Okay, but of course it is not really the so-called the noise lah. Okay, because it's still different from those noise which is introduced by the ambient environment, etc. This the association with the concept of noise is that such error will essentially occur random from sample to sample. The quantization of the quality of the quantizations is characterized by the signal to quantization noise ratio, SQNR. So quantization noise is defined as the difference between the value of the analog signal for the particular sampling type and the nearest quantization interval value. At most, this error can be as much as half of the interval. So it's impossible we have, entire, when we convert, let's say we convert 10 signal, all 10 signal corrupted by, fully corrupted by the quantization noise. This is not possible because, even though when you have sampling over here, the quantization noise only occur at this region, as the region, especially near the boundary lah. Okay, but all others values here would be correct. So it is impossible for you to get, when you convert a video, an audio to digital, convert an analog soundtrack to a digital audio, and then the entire soundtrack is being corrupted by quantization noise. It's impossible. Okay, it is still, most part of the information still useful and it is correct without the quantization noise. Okay, so that is why at most you can have half of the interval, which means mostly you have 50% only. You won't have more than that. So this would be the worst case of SQNR lah. Okay. I don't need you all to derive the mathematics algorithm lah, but at least you need to know SQNR is measured in dB, and the maximum, in worst case lah, the SQNR for each bit would be 6.02 n. N is the number of bit. So if let's say you have, 8 bit, so maximum noise that would be 6.02 multiplied by 8 lah. Okay, somewhere around this one. Okay. So the difference between the analog signal and the digital representation and arises as the result of the error in the. Okay, so this is what I meant just now. So of course, when you're sampling the data, this all are the district value, and the line here, the curvy line here is the analog signal. So all the quantizations would be happen here, here. So all this gap would introduce quantization noise. Okay. So, and also that is why it's impossible for you to have, the entire region, because all these regions are considered correct. All the information is correct. So it's impossible you have, full, your after the conversion from analog to digital, you have the entire audio being corrupted by quantization noise. It's impossible. Okay. But you are still inevitable to remove or to omit all the quantization noise. That is because the quantization noise will always happen here, somewhere around here, this region. Okay. So look at this one, this image. So the actual signal will be in black color, the sample signal is in red, and the quantization noise is in green color. Actually, the quantization noise, it is a bit weird, is that actually this is from here, obtained from here, and this is obtained from here. Okay, just that the authors try to compress the data, and you see something like this one, something like this one and this one, all this green color line. Okay, it is actually, this noise is actually from here, all the specky noise is from here. Okay. So when you have 3-bit, you have level is 8. Basically, it's 2 power of 3, 2 power of 4, 2 power of 5, and so on. With an increase in the number of bit level, the digital representation of the analog signal increase in fidelity and quantization noise becomes smaller. It is like you have more high, I mean, for example, you have a ruler and the ruler is only in one, I mean, actually increase in this bit is actually increase in sensitivity, which means you have a, a more sensitive measurement to quantize your audio. For example, you have a 2-bit 2-bit image. So within you have black and white only. So you only have black to represent the data or white to represent the data. But when you have a grayscale, you have 256 different color to represent a color value. So that is the difference over there. So when you have only 3-bit, which means you only have 8 level. When you have 16-bit, you have so many levels to represent your data to quantize your data. So that is why when you have a lower bit, your quantization noise will be higher. But you have when you increase the number of bit, the quantization noise will be smaller. This is this this theory will be used in audio processing in the next chapter. Because in the next chapter, uh, since we want to compress an audio, so we will try because we have very limited number of bits. So if you want to compress an audio, we will try to allocate the useful things to, I mean the useful bit to store the useful information. For example, now I'm very hungry. So the priority for me now is to get something to eat rather than buy a clothes, something like that. So we prioritize something else. So same thing over here. Uh, Later on in audio compressions, we will learn that how to identify which information is actually redundancy, and we will trying to reduce the number of bit allocate for those area, and we the rest of it which is important, I mean important information, we will migrate the bit number of bit from those which is not so important towards and give to those information which is more and more important. So this is how we manage the bit number when we have very limited data lah. So if let's say I have only 100 USD and I want to buy something, I need to prioritize my budget, something like that. So this is where we play around with the number of bit lah. Okay. So as SQNR to characterize the quality of quantization. So basically, SNR is to characterize the quality of the overall signal to noise. But SQNR is to characterize the quality of quantization. Okay, so for a quantization accuracy of n bit per sample, the range of digital signal is this one, which is from negative to positive lah. Excuse me. If the actual analog signal is from negative Vmax to positive Vmax, each quantization step is represented by this formula. Okay, because most of the time we have in sinusoidal wave lah, AC lah. So that is why we have negative Vmax and negative and positive Vmax, which is so-called voltage peak to peak voltage lah. Okay. SQNR can be expressed in terms of peak signal, which is mapped to V signal of this one. V signal of this one, which is this one, the denominator. So quantization of a waveform, plot of the quantization. Okay, this plot is just now shows in green color, where you only focus on the quantization noise, which is extracted from here, all this region. Okay, but we did not go in depth in this part, because this is require in-depth study to convert the quantization noise in only one graph. Okay, we don't include this one in the syllabus. So the peak SQNR can be then expressed as this one. Okay, so this is what I mentioned just now. This is the maximum SQNR noise can introduce to a system, and it is depend on the number of bit. If you have higher number of bit, of course the SQNR, the probability to have a high, I mean the worst case. This is the worst case. Okay, not a fixed case for quantization. I mean, at at most you can have this kind of noise. Okay, at most, and it is based on the bit number of bit. So 6.02 and if let's say you have 8 bit, so multiply by 8 lah. So in other words, each bit add about 6 dB because 6.02 is actually around 6 dB, right? So which means if you have a 16 bit provided a maximum SQNR at 96 bit dB lah, which means 6.02 n is equivalent to 6.02 multiplied by 16, you will get around 66 dB. So we have two types of quantization. One is linear quantization, one is non-linear quantization. For linear quantization is actually each and every gap is the same. Okay. Look into this one, you have all the staircase like the step function is the same. But for non-linear, it is different. Okay. Is that you can actually, increase the gap or decrease the gap. So in linear quantization, this is linear, which means all the interval are the same. You have mid-rise and mid-trade, which means step size is equal and fixed over time. SQNR follow the signal power, low SQNR for low level signal, and two common variation, mid-rise or mid-trade. Mid-rise mean rising edge is here, and this is not rising edge. Okay. In nonlinear quantization, small quantization step size is used when the signal is low, while large quantization step is applied when the signal is high. So to some extent, the nonlinear quantization would be better lah, because it can fit better to the because the nature of the analog signal is that uh, it is corrupted, not really corrupted, but many uncertainty over that. So you let's say you have something like this. So if you are using a linear quantization, you might have a lot of noise. But if you're using non-linear, you can actually map to the noise. You see, when you have a weak signal, so the interval is different. This one is different. So this is the benefit is that you can map better or fit better to the analog noise, analog signal, sorry. So in non-linear quantization, step size increase with signal amplitude and can be achieved by using quantizer with non-linear step size and compressing the signal followed by linear quantization. So advantage of non-linear quantization is that it improves the dynamic range and SQNR compared with linear quantization with the same quantization level. So I think this is linear and this is non-linear. So this is the difference. For linear, you only have a fixed gap over there, no matter for mid-rise or mid-fall or mid-trade. But for non-linear, you can fit better to accommodate different changes or different uncertainty in the analog. Is it very boring this chapter? I think you all is more interested in image, right? Rather than audio. It's okay. Yeah, it's okay. But nonetheless, for this part, uh, for the audio processing, I wouldn't say some calculation, but not many, some calculation only. Okay. But nonetheless, the calculation, yeah, the calculation is not heavy, don't worry about that. Okay. But it is still very important, because and anyhow, multimedia still cover the audio. Although in engineering practice, we seldom, I mean, at least not so famous in Malaysia Okay, if you go for the in the creative industry field, I mean in engineering in creative industry, for example, to create music and etc. Perhaps the audio processing is important. Okay, Okay, dynamic range. Dynamic range is defined as the ratio of highest to lowest non-zero value expressed in dB for the value 2n for an n-bit system, or simply state as the number of bits. This is the formula for dynamic range. The maximum absolute value for Vmax get mapped to this one, and the minimum is mapped to 1. So I will give you an example. Later on, I will have example. We can understand better using example. So Vmin is equals to the quantization step size given by this one. So the dr is again actually basically everything is measured in dB lah. When you involve audio, everything is measured in dB. Okay, so these are the different types of noise where you have the signal here, which is your amplitude, the spur, harmonic, and the quantization noise. Okay, perhaps if you have some other noise introduced to the system, you may have different kind of spiky there lah. Okay, so all those spiky you cannot really remove everything now because sometimes all these spiky can be your useful information. So for noise cancellations, actually you can have sort of filter over there. Okay, but of course, because usually your background noise is very low in volume and it may be very random pattern. So actually you can use maybe low pass filter to remove all this kind of noise, okay, which is in random manner. So amplitude refer to the voltage or current level of a signal at a given frequency. Always remember the signal is actually generated by using voltage, okay, a voltage change or the current change. So spur, also known as a device spur, as frequency component that appear in a signal because of the electrical component of the instrument. Some example of spur are leakage of oscillator clock signal and power insert by amplifier. So this spur is the noise that I mentioned just now, whereby whenever you have a you have a lousy speaker, lousy mic, or you have two mics put it together, so there would be external things which interfere your audio, but it is not from your audio itself, okay? Because the audio might be very good quality, very high SNR, but it still can corrupted with different kind of noise, but this kind of noise is because of the system itself. So we call it as a spur. Okay. So harmonic or harmonic frequency are frequency that are integer multiples of the fundamental frequency. Harmonic are often not part of the actual noise, but appear due to Nyquist sampling theory. So as you can see here, this is the end, this is the end, which means only here you will fulfill the Nyquist theorem now. So harmonic is actually it is always related to the Nyquist theorem. When you have Nyquist sampling until that level, it may introduce harmonic noise over there. Okay, but this is again it's not inevitable lah. You cannot avoid this one because you must obey to Nyquist theorem, else all the data would be undersampling. Okay, so noise will be all voltage and frequency components that are not present in the actual or ideal signal, spur or harmonic, but are present in the measurement or generation of test signal are noise. So basically, noise would be the terms that we all understand would be the random noise introduced during the recording or the conversion of the analog to digital signal. So dynamic range of a sound system is the difference in level between the higher signal peak that can be reproduced by the system or device. Um, because this is your spur, this image, I mean this chart, this graph is actually same as the previous one. This is harmonic and these are noise. Okay, so since the spur is until here, so this range would be spur-free dynamic range. Okay, so dynamic range would be the difference of level between the highest signal peak that can be reproduced by the system or device in the system and the amplitude of the highest spectral component, which means this is the highest peak that can be corrupted. Just like I mentioned, right, spur is the noise which is introduced by your hardware or system, right? Okay, so since this is the maximum peak, this is the maximum peak for your amplitude. So this level would be the dynamic range. Okay, let me repeat. Spur is the noise which is introduced by your system. Harmonic is the noise introduced by the Nyquist theorem. And this is the common quantization noise level. So dynamic range is the highest peak point from your useful signal or your amplitude to the highest peak point, which is the which is introduced by the system. So this range would be your dynamic range. Okay, which means you just get the amplitude of your of your system. I mean of your audio, and to get the amplitude of the spur, and then the gap between that would be the dynamic range lah. So SNR difference in level between the average signal noise and the average level of noise floor. So this is the signal to noise ratio, because at this level this is a noise, right? So this is your signal. So this peak point to this peak point, this would be your SNR lah. Okay, is it understandable? Okay, understandable. But anyhow, yeah. Basically, you just I'm not sure if you all still, yeah, never mind. That one is a bit. Mm, for this one, you only need to know what is amplitude, what is spur, what is harmonic, what is uh noise, what is quantization noise. So from here, you were able to determine the dynamic range, the SNR. Okay, but if later on, if you recognize something wrong, so perhaps you will get the answer wrong as well. But of course, I won't give you a chart. I won't just give you a graph like this one and then without labeling anything. Because this is not a must. I mean, this is not always a spur. Okay, this can be harmonic. Okay, because it is very dependent on the level, because the noise level wouldn't be fixed over there. It's impossible for a noise to fix over there, and impossible you have a same amplitude for any different audio. So if in case chart like this, I mean a figure like this is being displayed in your one of your examinations, for sure there will be labeling. Okay, so I would label this is what, this is what, this is what, and this is what. So later on, you all can answer according to the label. Okay, but of course, if I asking for dynamic range, you give me this gap, for sure is wrong lah. Okay, something like that. So of course you need to know which part is dynamic range, which part is SNR, something like that. So example one, what is the dynamic range if the signal is in the range between negative 5 volt to 5 volt, which means 10 volt P to P, peak to peak, and 8-bit quantization is used. Okay, try to figure out what is the calculations. I mean, now I'm asking for dynamic range. What is the dynamic range if the signal is negative 5 volt to positive 5 volt with 8-bit quantization? Okay, refer back to the formula in the previous slide. Okay, so this is actually very simple. It's super simple. So you have your Vmax, Vmin Vmax. So basically just put in 5 volt and divide by n is 8 bit. So you have Vmax is 5 volt divided by 2n minus 1. So n is 8, which means it's 2 power 7. Okay, resolve this one, you will get this one. Okay, and from here you will able to get the V mean and refer back to the DR dynamic range. Dynamic range. This one, dynamic range. Okay, so 20 log base of 10 Vmax divided by V mean. So you have a Vmax as 5 volt. So 5 volt divided by the value V mean which you obtain over here. So you will get your DR lah. Okay, this is how you get. But you have to know the formula because the formula is not given in the examination. Okay, usually the formula because this is not something Ohm's law V equals to IR or all these common formula is not given in the formula. I mean as attachment in your examinations. Okay, so that's all. Channel. A channel correct. A channel is like stereo, mono. Those are channel. Perhaps now we seldom exposed to this. Except you have your own your boss system in your room or whatsoever. Because last time we have so called the radio, the radio what so called what put in CD and then something like this one very you have a lot of different controller and then you can put your CD, put your cassette over here. I'm not sure if you all ever see this in real. Not so. Maybe you only see this in those cafe, those vintage cafe for you to snap, you know, snap photo. I'm not sure. Have a last time we really have this kind of things. So we can put in the cassette, you can put in the CD and etc. So for this kind of radio, it's very common for you to select a mono or stereo. Okay, but some only mono lah. Okay, it depends. But actually, this is very uh, common in those radio. You're able to see this kind of parameter for you to select. So a channel correspond to a stream of audio data, both input and output. So recording only one channel is called monophobic or simply mono, and two channel is called stereophobic or called stereo. Different channels are sent out through different speakers, giving the sound more dimension as if it is come from different places. The popularity of multi-channel audio is also growing. Basically, mono and stereo is like you have one. This is mono whereby you have one signal sent to different speaker, which means both side of the speaker is the same things. But for stereo, you have different signals sending out, which means you have for example, your earpiece, you have left and right, right? So when you only put in the left side without the right side, the signal is not, I mean, some signal wouldn't be able to listen at your left or at your right corresponding respectively. This is actually like, you go for cinema to watch movie and then you will found that, oh, the main character is walking in the bushes and there is, eagle fly, I mean, across the sky, and then you were able to heard that the noise is coming on top of you, something like that. So actually, if uh, this way is that you have different kind of signal to be portrayed to this audience. I mean, a group of audience. Let's say this is the cinema, the audience seat. This is the screen. So you have your different signal portrayed to different area. So this is how how we call what Adobe, what IMAX or what whatsoever lah. When you go to cinema, you have different ranking of ticket, right? So some is what max audio or whatsoever. Actually, these max audio are the benchmarking for a different setting. For example, you have audio A. So when you go to this kind of cinema, the setting is in audio A setting. If you go for example, Adobe, so they have their own very own setting over there. So those kind of setting, the name is Adobe. Those kind of setting is known as Max or IMAX or whatsoever, something like that. So that is the name lah. But actually, this name is reflecting how they set up the entire cinema, how they put the audio system, the audio system and etc. So that is why when you go for different ranking of audio level, you will find that the sound is coming from different direction. It's like you are in that position as per the main character. Okay, so this is the difference between mono and stereo. Mono would be one signal. I mean, one audio. Just you just simply multiplying the source only lah, which means you have the same old signal, just you play over here and play over here. Both sides is the same. But for stereo, you have signal 1 and signal 2, whereby signal 1, when you listen, maybe you cannot listen some background noise. But for signal 2, there is background noise over there. I mean, not background noise, but like someone talking in the background, someone talking, mocking the footstep from far away, something like that. So this would be the main and this would be the core, something like that. So that is so-called the mono and stereo. And mono and stereo is actually referring to two lah. But now we have a multi-channel lah. Okay, since we have especially in cinema, we have multi-channel. You have one under your screen and two at the side there. This is the most cliche one. And another one would be just on top. I mean, behind the audience seat there, something like here. So this would be the setting. Different setting, you have different name, and all this name is being so-called there is a copyright over there lah. Okay, if you want to have this standard, you must have such kind of audio system. You cannot just simply say, oh, I have a Mac what iMac system over there, but actually you don't. But because people will come and check and get the license from there. Okay, so that is so-called the channel lah. Okay. So true stereo means sound recording and sound reproductions use stereographic projection to encode the relative position of the object and event record. Okay, so this is a very meticulous task because when you do recording, you need to characterize the sound into different signal. Okay, which means you have a bunch of, one basket, and in each basket, you need to label everything in the basket, something like that. So later on, you can say, oh, this one go first, this one goes next, something like that. You can partition the signal. So that is why you have to label it first. In a common stereo setup of two channel, left and right, one channel is sent to the left speaker and another channel is sent to the right speaker. So that is very important for you, for the manufacturer to label which one is left, which one is right. Because when you interchange, the effect will be greatly reduced. So by controlling to which channel you send the signal, you can control the position of sound. This is the most very important because we always want to control the position of sound to enrich the engagement of our senses towards the multimedia. Okay, so that is how when you go for Disneyland, there's 4D or 5D. Even your chair is moving when you're running the main character is running in the bushes. You can feel there would be some vapor, some coming out. All those are being put in the position so that you can feel as you are in the storyline, something like that. So one will hear some sound coming from different directions, depending on which speaker you send the signal to, or in which proportions. One can send just a little more to the right speaker so that the sound is positioned just a little bit to the right. Okay, so this is just meant to position the sound lah. You want to cater or tailor the sound in order to enrich the engagement over there, and sound with equal proportions on both speaker will appear to come from the center. So basically that is you just play around with the amplitude. If you put the intensity is greater at the right hand side, you will feel that someone is coming from the right hand side. And if both sides is equivalent, you will feel that something is coming just in front of you, which is impacting you. In other words, stereo opens the possibility to play or playing with sound localization. Localization which means you position something else to a specific position. Okay. sampling and data rate. Okay, before we proceed, we take 5, and then we proceed for this one. Okay, so we continue with the sampling and data rate. I plan to finish this chapter by today, and for the next class, we will go for audio compressions. Okay, so sampling and data rate. Yes. One moment. Yeah, because this one is just to display. Okay, sampling and data rate. Sampling rate is how many sampling rate is actually rate is actually referring to rate is actually referring to uh the number of time, right? The how should I put this? Rate is the rating the rating you perform a sample. So sampling is an action, is a verb as well. So sampling rate is actually how many times per second an amplitude of the analog signal is being measured. The amplitude here may or may not referring to a peak lah. Just how many times you take a sample lah. No matter is it peak or bottom, no matter is it until here whatsoever the amplitude it is, just that how many times you perform the sampling. So resolution is the number of discrete value it can produce over the range of analog value. Audio compact disc, which is CD, use 16-bit quantization, which provide this value. So as we learned in previous slide, the higher the number of bit, which mean would have a lower value of quantization, because it is like you have 2-bit, which means you have black and white color. So that's all you can use to represent your pixel. So if you have 16-bit, which means you have more color pixel to represent your data. Okay. So since you have 16, your quantization noise would be lower, but to the worst case, it is 6.2 n dB. Okay, this is the worst case. So which means 6.2 multiplied by 16, you will get around 96 something. So okay, so as I mentioned previously, the x-axis is time, the y-axis is your amplitude, and in x-axis we will call it as sampling, and in y-axis we call it as quantization. Okay, this one is last week lecture we already mentioned this one. We don't really call sampling at the amplitude lah, but we call sampling in terms of time interval. Okay, so this is the sampling and this is resolution. Resolution, you can also describe it as an amplitude or intensity whatsoever. Okay, but it is more towards to measure the peak lah, the value to get the sample. So A and B, this is ABCD. A and B have the same sampling rate. Same sampling rate, which means the time taken for you to take the sample, but different resolution. This is only 1, 2, but this has 1, 2, 3, 4, 5, and so on and so forth. Okay, so A and B have same sampling rate. The x-axis, the x-axis, the gap in the x-axis is the same, but the y-axis is different. B and C have same resolution but different sampling rate, which means for B and C, you have same y-axis interval, but the x-axis interval is different. Okay, the sampling rate in C is higher, and C and D have the same sampling rate but different resolution. C and D, you have same sampling rate but different resolution, which means the resolution is much more higher lah. Okay, but the sampling rate is the same. So always remember, sampling is referring to the x-axis, quantization is referring to the y-axis. Okay, so you have yeah, just to the main purpose of this is just to let you all know different changing the sampling rate or changing the quantization rate would affect the quality of your data. The uncompressed data rate increase as more bits are used for quantization. For example, that is the higher the number of bits, the higher the uncompressed data rate. Number of audio, for example, stereo or mono, also greatly increase the bandwidth required. The data rate can be calculated using this one. This is the data rate, sampling rate multiplied by bit per sample and the number of channel. So we have three different things affecting the data rate. One of it, sampling rate, how fast or how frequent you take the sample. The second one, bit per sample, 8 bit, 16 bit, or 32 bit. Number of channel, mono or stereo. So this is the example. Calculate the data rate of stereo audio CD using the information as follow. Of course, I wouldn't test your memory lah, but you should know CD is 16 bit lah. Okay, you should know CD is 16 bit. And what is stereo? Stereo is equivalent to how many channel? You should know lah, this one. So try to do this one. The data rate, okay, this is the data rate formula. Okay, so let's look into this one. The data rate is simply the sampling rate multiplied by bit per sample and number of channel. So you have a stereo, so which means you have two channel. You have CD, which means you have 16 bit, and the sampling rate is given, which is 44.1. Actually, of course, I did not really test on this one now, but actually, 44.1 is actually same as 44.1 is actually double the minimum uh, uh, audible audio where a human being can receive. So let me recall. I think the minimum human can hear is around 20 hertz. So this is the maximum 20 until 20 kilohertz, I think. And this is double of the maximum. Okay. Oh yeah. 2 times upper limit. Upper limit is around 20 kilohertz, I think. So this is 2 times upper limit hearing capability. And we have 44.1 kilohertz. Bit is 16 bit. So the data rate would be the sampling rate is the 44.1 kilohertz and 16 bit given by CD stereo. So you have two lah. So this would be the answer. Okay. So make sure you give your answer. I mean, whenever you perform the calculation, always remember to give me the correct SI unit. If you give me the wrong SI unit, I will deduct maybe 1 marks over there. Okay. But let me think. As far as I concerned in engineering, if you did not give any SI unit is 0 mark. Yeah. But don't worry, you still will gain your mark in your solutions. Okay. But nonetheless, a wrong SI unit or no SI unit would be equivalent to no marks. Okay. But some, of course, some is without SI unit. Okay. But I don't think we have a lot of different calculation in MTAA. So should be no issue. So example 3, a narrow band speech signal with a bandwidth limited to 0 to 4 kilohertz. Determine the sampling rate and sampling interval. Of course, I know you all have the lecture notes, but try to do lah. Okay. Hmm. One moment, let me calculate first. Okay, thank you. For the previous example, should be 1.412 mega Mbps or 1411.2 kbps. I put the, yeah, I think I put this wrong. I will amend later on. Thank you. Okay, let's see example 3. A narrow band speech signal with a band width limited to 0 to 4 kilohertz. Determine the sampling rate and sampling interval. So in order, based on the Nyquist theorem, if a signal is a band limited, which means you have a band, upper limit and lower limit lah. Okay, so 0 to 4 actually is equivalent to 4 as well lah, because f2 is your f2 is 4, f2 is 4, and f1 is 0. So 4 minus by 0 is 4 lah, and multiply by 2 is 8. So the second the sample interval is 1 divided by 8 kilohertz. You will get this one. Okay. Actually, I think this, for this example, you only need to know the definition of Nyquist theorem, and then you can actually perform this one without the formula. You don't really need a formula to get a sampling interval, because as far as you know, the sampling interval is always the same. Okay, that it's impossible to have a sampling interval which is irregular. Okay, but it is important for you all to know the Nyquist theorem. It's important for you all to know the Nyquist theorem. It's important for you all to know the definitions. Okay, the data rate and the bandwidth in some audio application are as follow. This is just for your information. I don't think you need to memorize it. Uh, Nonetheless, if for example, if the question asking for a telephone, I would give you all the number of bit. I wouldn't expect you all to memorize what is the telephone, the bits per sample for telephone. But for the image processing, I wouldn't give lah. For example, a binary, you should know is 2 bit. RGB, you should know is 24 bit, something like that. Okay, it's not possible. I mean, that would be so common already. Okay, so those I wouldn't give you lah. So telephone, which has a sampling rate around, similar is as kilohertz, 8 kilohertz. Bit per sample is 8, and these are stereo, and this is up to 6 channel. Um, Mono is 1, stereo is 2. Stereo doesn't mean multi-channel. So if let's say it is more than 2, it would mention the number of channel. For example, 3, 6, 7, something like that. Stereo must be 2 lah. Okay. So this is a data rate if compressed and signal bandwidth lah. Okay. Anyhow, this is just FYI. So the best way to judge the quality of an audio file would be the bitrate. So audio file bitrate are measured in thousand of bit per second. Thousand which means kilo lah. Thousand which means kilo. When audio is converted to lossy file, its bitrate is much lower. A higher bitrate is better. So 256 kbps MP3 or AAC file is better than 128 kbps file. Of course, it is better lah because you can store more and more information. But nonetheless, you require a larger size for to store the particular information. So for lossless file, its bit rate depends on density and volume of its music. For example, two tracks on the same album read to a lossless format have bit rate of 400 kbps and 900 kbps. When they play back, they reproduce the original audio from CD at the same level of quality. So the data rate is actually this is a sample. This is the equations. Sampling rate multiplied by bit per sample and multiplied by number of channel. So 1 byte is equal to 8 bit. This one have to be memorized because I will not give you all this one. If let's say the calculation of size is required in your examination, you always remember 1 byte is equivalent to 8 bit and 1 kilobyte is 1024. Okay, always remember this one. Don't, I mean, try not to lose your mark because of this kind of minor mistake lah. Okay. Data rate give amount of data generated by the encoder per second. Okay. So the first row, the first column at the left hand side, application requiring an increased audio quality and frequency bandwidth. Yeah, this is just for your information. Okay, you don't need to memorize this one. For telephone, data rate, sampling rate multiplied by bit per sample multiplied by number of channel divided by 8 bit because telephone has 8 bit. Oh, sorry, 8 bit here. So for FM radio, divide by 8 bit as well. Why 8 bit? Why not 16? 16, 8 bit. One moment, let me check. Oh, okay. This is bit per sample, but anyhow, it is divided by 8 bit because you want to force into 256 uh, information range. But the bit here is referring to this one, bit per sample. Let me remove this first. This is the bit per sample. So for telephone, you have 8 bit here. And for FM radio, you have 16 bit and CD, you have 16 bit. Okay. Basically, this is to for per second. Okay. Because you always store in 1 byte, right? Can you all recall? This is the equation that we learned just now. Okay. And why is divided by 8 bit? Because we want to convert to byte. Okay. We always divide by 8 bit because we convert to 1 byte. And then 1 byte, we can later on convert again to 1024 to become kilobyte, something like that. Okay. So this 8 bit is not referring to bit per sample. The bit per sample should be put into bit per sample here. Okay, so for CD again, you have a 16 bit and then you have a stereo and this is the frequency lah. So divided by 8 bit because you want to convert to byte. Okay, that is why you have BPS byte per second. So a higher quality digital audio implies that audio signal is perceived similar to the real analog sound before being digitization. So that is why as I mentioned in last lecture, when I speak to you face to face, the intonation, the voice that you heard would be different where you hear my voice through the online platform or via the phone call. That is because that is because the that is because when I call during using the phone or any other virtual platform, the sound wave itself is being digitized and introduce different kind of quantization noise, spur, harmonic, and etc. noise towards the original audio. Oh, sorry, original soundtrack. I mean the analog lah. Okay, so that is why you would have a uh, different sound over there. But nonetheless, you will still able to understand the information because the information still encrypted over there, which means I still have the same pattern, just that maybe my waveform, my sinusoidal waveform or whatsoever waveform, but a continuous waveform, analog waveform, will be a big difference. Okay, that is the differences between the digital audio and also analog audio. But if you are using a high quality digital audio system or algorithm, you would be able to uh, I mean, very difficult for you to differentiate between the analog and digital lah, because the quantization, the spur, the harmonic, the harmonic noise, the all the other background noise is very low in ratio. So digital audio quality can be increased by increasing bit per sample, sampling, and number of channel. Actually, all these three is from the data rate. Okay, all these three item is from the data rate. You don't actually need this bullet point to know that how to increase the digital audio quality, because the data rate itself telling you what is the core features required in the data. To increase the overall quality. Okay, so first of all, you bit per sample. The higher the bit, the more the information the audio can hold. So you have a more, rich information to present. Sampling rate, if you're sampling something else in higher frequency, of course you need to obey the Nyquist theorem. For sure, you have a better data representation, but of course your size will be increased. So that is why you have all these items multiplied together, right? And number of channel. If you have multiple number of channel, you would have a better uh, engagement, sensors engagement. So stereo audio use two channels to represent left and right source as to produce a more realistic sound to the human ear. Surrounding more channel. So in a cinema, basically you will have surrounding sound, one in the front, one in the back, top, left and right. So you would be able to enjoy a more different dimensions sound location. And increased quality will increase the data rate and therefore data size. This is very important. You have to correlate this one. Of course, everyone wants to have a better data rate, but of course, you will have your data size increase as well. So that is why in the next chapter, we will come to audio compressions. Okay. Increased quality will increase data rate and therefore increase the data size, which is the last logic lah. Okay. This one is actually applicable to audio, video, and also image. Okay. One moment, let me open the another lecture notes. That's all for the chapter 8. I have uploaded the chapter 9 in the Google Classroom as well. So for today, I think I will give you an introduction. For the next two chapter, starting from audio, we will learn audio processing, audio compression. And for the next two chapter, in total we have 11 chapters. In the next two chapters, we'll learn video processing and video compression. That's all. Okay. So we have 11, 3 to go. Okay. As I mentioned in the early of this semester, the multimedia is meant to engage human being. So for no matter in image compression, audio compression, and video compression, we are trying to explore the perceptions of the human being. So since our human eye is not so sensitive towards high frequency information, so we tend to remove high frequency information during the video compression. Video and also image compression. But of course, in video compression, we will have further compressing method, because video is actually time dependence and also time independence. So called time dependence is that you play your video across a different timeline, right? But when you break down the video, you can saw you would have a different frame. So frame would be a static data, and the video itself, I mean, combine all the frame would be the time dependence data. Okay, so audio compressions. Introductions to audio compression. High data rate such as CD, which has a 16-bit. This is the 4.32 mega Mbps, are incompatible with internet and wireless application. So audio data must somehow be compressed to a smaller size, which is less big, while not affecting the signal quality, minimizing quantization noise. So sometimes we need to upload something else, especially when we are like a Google platform, we are performing recording, and then we actually need to cater two different things, the audio and the video. Usually when we just mention the video alone, we did not include the audio. Although video mostly come with audio. I mean, for sure you have the sound, okay? But actually, when we do compressions, we perform the compression different. Okay, I mean, in not using the same algorithm. Okay, the algorithm used to process, I mean, to compress the video itself is different from the algorithm that you use to compress the audio. So parameter that determines the memory size and bit rate of audio data. So this would be the four parameter: some sampling rate, sample per second, resolution, bit per sample, and number of channel, which is stereo, mono, or multi, and the duration of the play audio. So how to reduce the audio data? Lower the sampling rate. Actually, how to reduce the audio data is that, just now the data rate is to how to improve the quality, right? So we'll just in previous slide, you are going to increase everything, right? For this one, to reduce audio data, you just decrease everything. Okay, but it's impossible for you to decrease everything beyond the minimum level, because if you decrease everything to beyond the minimum level, you will no longer able to understand what is the audio meaning to you. Okay, so lower sampling rate, lower channel count, and lower resolution. Okay, lower sampling rate is, always remember the x-axis is the time, and it is about the sampling rate. The y-axis is about the amplitude and about quantization. Okay, so or somehow we call it as resolution. So if you lower the sampling, which means you reduce the sampling rate. But of course, you cannot against the Nyquist theorem. If you against the Nyquist theorem, the entire data would be irrelevant. I would say irrelevant. Okay. And the resolution, if the resolution is too coarse, which means it cannot really, if your resolution is too coarse, so your quantization noise will be very high. Okay. For example, you only have two levels, which means this is one level, this is second level, something like that. If you have more, if you have sampling and more data rate, for example, you have so many samples, but you have only two. This is your signal. So this would be 0, 0, 0, okay, 5. This like 1, 2, okay. You will able to get this one, and then the rest will be here. And this will be 0. So after all, you will get something like this one, which is not really representing your data. Okay. So this is the effect of resolution. So if you have better resolution, so you can plot somewhere around here. If without the resolutions, for example, this one is not yet achieved number 2, but somewhere around this gap, it will fall until this one. Okay, so this is the effect of low resolution. As an alternative, use data compression. You can still enjoy the sampling at a high sampling rate, better channel, more channel count, but you and with a good resolution. So later on, after you perform all the sampling and compile as a video, you perform data compression, which means you compress the data later on. So recall back, digital audio data is actual representation of the sound stored in the form of sample. Digital audio is the, representing or approximate the digital audio, but you digitize it. Sample represent the amplitude. Sample represent the amplitude of sound at the discrete point in time. So the quality of digital recording depends on the sampling rate, the sample taken per second. Okay, so this is according to the Nyquist theorem and also the data rate as well. Two main principles in compression: remove redundancy and remove irrelevancy. Audio compression algorithms are used to obtain compact digital representation of high fidelity audio signal for the purpose of efficient transmission or storage. So the MPEG motion picture expert group, in image we have JPEG, right? In here we have MPEG. So MPEG and JPEG are two different expert groups, right? Okay. JPEG is for static image, MPEG is for motion, which is video, and audio compression algorithm is the international ISO standard for high fidelity audio compression. So basically all of these JPEG and MPEG are under ISO. I'm not sure you all know about ISO, but ISO is International Organization of Standardization. So it is meant to standardize all the, not all but I believe most of it most of the, it is sort of like the WHO When the pandemic happened, the WHO is the one who is the core who speak for the world in terms of health. And you have UNESCO for different kind, World Bank Association and etc. So these are the international. But for this ISO is the international organization specifically to address the to standardize something else. For example, QMS, quality measurement system. For example, the safety. They have so-called the ISO ISO 9001, 2015, ISO 4500, I think it's 2018. So these all are ISO. If you want to gain competency in ISO, you need to take exam. You need to take exam to become the auditor. You need to take exam to become the auditor and then lead auditor, something like that. So every company needs auditor because in order to against the bribery, one of the campaign by the government. So we will always need auditor no matter in what field. Every field, eventually the university, we need auditor. So if you have knowledge in terms of ISO, which means you can be employed by all the company, almost all I would say. So PCM, pulse code modulation. In pulse code modulation, I think I give you, okay. PCM pulse code modulation. Techniques analog input signal information is converted to a binary code, which is 1 and 0. As I mentioned previously, we did not really learn into the in-depth. Is that actually when we deal with multimedia system, we are dealing with computer science. So if you are dealing with computer science, you are dealing with 1 and 0 only. Okay, but we don't really learn into that depth. Is such that we only learn the theory, how to perform the JPEG compression, how to perform the video compression and audio compression. But we did not really learn until how you generate the binary code, which is 1 and 0. Okay, but of course in Harmonic coding, in JPEG, I did mention until how you get the 1 and 0, because I think that is quite important. But anyhow, that is also the reason why I did not give you all the full table of 1 and 0, the Harmonic coding table, is that if in case you all need that, appear in the examination, at least you all know how actually this philosophy is being used, how you actually get 1 and 0 based on what theory, and that's all. At least you heard about the Harmonic coding and etc. Okay, but actually, it's important for you to know but I don't think you need to know that explicitly, because nowadays everything is being computerized. So basically, you just need to
everything computer will settle for you lah. I mean, JPEG is a very cliche and very stable algorithm already. So, but it's good for you to know is that you will able to know what information being abandoned during the JPEG conversion, during the MPEG conversion, during the audio conversion, because you may need this information or this knowledge in order to innovate something else in different industry. Okay. So PCM, the PCM is the technique is analog input signal information to convert to binary code, which means PCM is actually you can actually see PCM as ADC like analog to digital converter, which means you originally have an analog signal like this one. After the PCM, you will convert to binary. Okay, the binary signal is like a step signal. This step signal is actually sampling like, okay, just 1 and 0, 1 and 0, something like that. So this would be the sampling data. The first column at the left-hand side will be the sampling, quantization, and encoding. Okay, so first of all, you need to perform sampling and quantization. Sample at twice the highest voice frequency. So this is twice the highest voice, which means you obey the Nyquist theorem. And then round off the sample to one of 256 level. As I mentioned before, you only you need to convert to 8 bit because you always divide by 8 to become byte, right? So you need to fit into 256 level, and then later on encoding, you will get this kind of coding 1010. Okay. Okay, I think I end here. We will continue in Thursday. Okay, any question before we end? If no, so that's all for today. Thank you and bye-bye.